Hello everyone, my name is Pan He and I'm a graduate student at ECE Department, University of Florida. This presentation is for the Network Science and Applications course. I want to thank Dr. Wu for this excellent course. My title is Generating Face Image Using Neural Network. So what does it mean to generate face image? Here we intend to create data from scratch, like generate data with Gaussian noise. In machine learning, it is called generative model. Generally, we have discriminative modeling and generative modeling in machine learning. The discriminative modeling aims at assigning a label to the input, such as scene classification and face recognition task. It focuses on finding the boundary between the dataset. And the generative modeling try to create data with random vector input, such as to generate a scene image or a digit number. It tries to model the distribution of individual classes. These are some examples for discriminative modeling. As you see, like this one. It makes the classification and tells us this is a city street. And on the right, the face recognition model will tell us who the person is. These are some animation examples for generative modeling. As you can see it, the model are trying to simulate the real data and make it as real as possible. In generative modeling, there are some excellent researchers. One of them is Goodfellow. He proposed a classic model called generative adversarial network. We call it game model. This network creates a competition between the discriminator and the generator. The basic idea is that the discriminator will tell us whether this input is real or fake, and the generator will try its best to generate data as real as possible. Namely, it tries to fool the discriminator into thinking that the generated data is real data. Thus, the overall function is pretty straightforward. It's a min-max function. This function will encourage the generated data to have the similar distribution of the real data. We can use a figure to illustrate it. There, the blue dotted line is this discriminator. At the beginning, it can easily distinguish the real data and generated data. The black dotted line is the real distribution for the real data, and the green line is the distribution for the generated data. As you see, with more training iterations, the green line starts to fit the black line. That is to say, the generated data become more and more real. Thus, the discriminator cannot distinguish the generated data. Now, as you see here, the discriminator curve become flattened. And this flattened curve is actually the final goal of GAN model. The naive GAN model only takes the random inputs, which means we cannot control the generation process. Suppose we want a data similar to a certain person. We cannot do it with the original GAN model. What if we add some additional information? Like we tell them to generate any picture. And this is called conditional GAN model. The equation is very simple. It directly modifies the original GAN model function by just add an additional conditional variable L in as the input for both the discriminator and generators. With this simple modification, we can get the GAN model to generate what we want. As you see, we can use it to generate lots of bedroom scene images. The conditional GAN model also opens another gate. When we do supervised learning, we always want to get more data with label information. However, it is cost and non-trivial to label the data. If we can use the CGAN model to generate some realistic data, the label information for each sample is already there. It will save us a lot of resource. Conditional GAN model is very interesting, but it fails to generate a large image since it has some limitation on restore the image details. Fortunately, in image processing, there is one method called Laplacian pyramid. It decomposes an image through multiple details layers with at different scales in a pyramid-like fashion. In each layer, it will restore some details, or called image residuals. By doing this, it can exaggerate some details for the image. Inspired by this, the Laplacian GAN model replaces each residual image layer with a CGAN model, a conditional GAN model. Allow a Laplacian reconstruction with GAN model. In our experiments, we also use this architecture. This is our discriminator and generators. The discriminator is a widget like the convolutional network, and the generator is a deconvolutional network. And there are some tricks. In the generators, we add some batch normalization because we want to speed up the generator, since in the reality it's harder to train a generator than to train a discriminator. And we also use a single mode layer in the end of the discriminator to make the network easy to saturate and intentionally make it slower to converge. This is the algorithm to control the training. We set a mapping threshold. When the training errors is less than the threshold, we may stop the discriminator. And when the error is higher than a certain threshold, we stop at updating the generator. That is to say, we control when to update the discriminator or generator. This is the main class accuracy. The left figure is for training and the right figure is for test. According to our computation, the accuracy curve is near the theoretic results. After training, as you can see here, we can get more present image with more iteration. Now I'll show you how to run the experiment. All the experiments are conducted in the torch framework, and I'll show you how to run it. We conduct the experiments on the LFW dataset. It's a popular dataset for face. Now, training is please. As you see here, we start to train the network, and the parameter will stored at this. Like we have some log file. So here, in the beginning, the game model cannot restore anything. After this is the second approach, it starts to find something. Then, with more iteration, as you see, the face is more clear. Like about maybe choose. As you see here, it's more present. These are the picture during the training. We can also do some testing. The testing will load the trained model and randomly generate some Gaussian input. Then we generate lots of face images. As you see here, this is some randomly generate images, face images. Okay. So we present architecture to generate face images. And in the experiments, we also explore some tricks such as batch normalization and how to set the threshold to control the whole training process. Thank you.